Hello AP Chem students and welcome to topic 8.11, pH and solubility. The learning objective for today is 8.11.a, identify the qualitative effect of changes in pH on the solubility of a salt. So this is the last section that is truly on equilibrium in the course. It is a nice culmination of equilibrium because it brings together a couple of things we've been talking about into a tidy little unit. So the pH of a system can affect the solubility of a salt in that system. So remember that low pH means there are excess H plus ions and therefore few OH minus ions, whereas high pH means that there are few H plus ions and therefore excess OH minus ions. If you keep that in mind, then the solubility, depending on pH, becomes an obvious application of Le Chatelier's principle. So let's consider magnesium hydroxide for a moment. So in the solubility of magnesium hydroxide, the solubility is affected by pH. So if you have low pH, the added H plus combines with the OH minus to form water. So H plus OH minus yields H2O liquid. Now remember that liquids and solids do not impact your K expressions, and so forming water basically removes this from having an impact on equilibrium. This reaction here, the synthesis of water, decreases your concentration of OH minus. And so if you remember here that your K expression would be the concentration of Mg2 plus times the concentration of OH minus squared, if we decrease your concentration of OH minus, you're going to decrease your Q. So then that would mean that your Q is going to be less than K. Your equilibrium is going to proceed to the products, shift to the products to reestablish that value of K, and therefore you're going to increase your solubility. Now let's look if you had a high pH. If you have a high pH, you're adding OH minus, and therefore we essentially have a common ion situation. So you've increased your concentration of OH minus. That means that your Q is now going to be greater than your K, and so your equilibrium will then proceed towards your reactants, and that would decrease your solubility. So let's think about this in terms of equilibrium shifts. So this can also affect ions that are strong conjugate bases that therefore will combine with H plus ions to make a conjugate acid or a base ion. So here's a generalization for you with that. If the anion X minus is part of a weak acid, meaning it's a strong conjugate base, then the salt MX will have an increased solubility in acidic solution. I'm going to show you what that means. Generally, you need to think about the pH dependence of a salt if one of the components is the conjugate of a weak. Okay, so if it's a relatively strong conjugate, then you have to think about pH dependence. So let's look at CaF2. All right, so CaF2 will dissociate into Ca2 plus 2F minus. Now, this is a cartoon drawing of what that would look like. This does not represent the actual K value because I haven't shown any perspective in terms of quantities that you're starting with or anything like that. But we're just going to go with this illustration to help you understand what's happening here. So you can see we don't have a common ion, like there's no OH minus like we saw in the previous slide. However, let me move my face here. So if I'm going to do a little counting for you. So to start with, we have Ca2 plus of 3 and 2F minus of 6. Okay, so then this generalization that I told you holds true because if the anion will combine with added hydrogen from solution, so if you add acid and you have that H plus ion, what can happen in this particular case is it can form the weak acid, okay? So this would cause a shift of the equilibrium towards that ion because you would be removing the ion by forming the weak acid because it's the conjugate. Let me show you. This will make more sense. So in this situation, if I add H plus, I lower the pH and adding H plus, it can combine with F minus to form the weak acid HF. HF only partially dissociates. So if we add some acid, we would expect at least some of it to combine with the F minus to form that weak acid HF. And so you can see that this is what it would look like here. And so then what happens is by adding that H plus ion, we are decreasing our concentration of F minus. The HF does not appear in this equilibrium up here. So by forming that HF, we have removed some of the F minus and that then changes our Q value. And so now our Q value will be decreased relative to our K, and that will cause the equilibrium to proceed towards the products. Okay, so I think this will make a little bit more sense if I show you some examples. All right, so I have 4 examples for you. This is practice number 7. So which of the following salts would have solubility that is impacted by a change in pH? So we have ZnOH2, KBr, Na3PO4, and PbC2H3O22. So go ahead if you want to try these on your own. Pause the video now because I'm about to go through the answers. So we're going to take these one at a time. So we'll start with the zinc hydroxide here. And so then this will be more soluble in acidic solutions. So you have the dissociation equation here of zinc hydroxide is in equilibrium with zinc 2 plus and 2 OH minus. So what we can see here is that this OH minus is the part of the dissociation that will be impacted by pH. So if we add acid, that would combine with the dissociated OH minus like this to form water. And again, remembering that liquids don't impact equilibrium, so we are removing OH minus from the equilibrium system here. That reduces your concentration of OH minus. It decreases your Q. Because your Q is less than K, your reaction will shift to the products, which increases the solubility of zinc hydroxide. Now, if you were to add base to this system, then again, as we talked about in the previous slide, that would be a common ion of hydroxide, and so that would shift you towards the reactants, which would decrease your solubility. All right, so now let's look at KBr, and KBr is not impacted by a change in pH. So the dissociation equation for KBr is K plus Br minus. Both of these are conjugates of strong species. So K plus is the conjugate of KOH, which is a strong base. Br minus is the conjugate of HBr, which is a strong acid. So if you add H plus or OH minus, you're not going to have anything that is going to remove your K plus or Br minus from your system, and therefore neither is going to be impacted by the change in pH. Sodium phosphate, if we look at this, this is going to be more soluble in acidic again. The reason for this is that your dissociation equation is 3Na plus PO4 minus. PO4 minus is the conjugate base of a very weak acid, which is HPO4 2 minus. And then that is also the conjugate of a weak acid, H2PO4, because PO4 minus, because these, of course, can go all the way to phosphoric acid, which itself is relatively weak, but this is an extremely weak acid. So, adding H plus ions will cause the formation of HPO4 2 minus, and then therefore that would remove your phosphate ions from the solution because it would form hydrogen phosphate. That would decrease your concentration of phosphate, lowering your Q, making your Q less than K. So the reaction will proceed to the products to reestablish equilibrium, which increases your solubility of sodium phosphate. All right. Now, if we were to add a hydroxide here, if we were to make this basic, we wouldn't see a change in the solubility because the sodium hydroxide here is a conjugate of a strong base. So we would not expect adding hydroxide to impact this equilibrium at all. All right, finally, lead acetate. So lead acetate, once again, will be more soluble in acidic because we have this acetate ion. Whoops, I forgot to change this. Hang on. Okay, there we go. So your acetate ion is the conjugate base of a weak acid, acetic acid. Adding H plus ions will cause the formation of your acetic acid, thus decreasing your concentration of acetate, lowering Q, and making Q less than K. Now, you might be wondering, in what situations would we be more soluble in basic? And this probably makes sense to you. So we looked at examples of things that are conjugates of weak acids. If you had the conjugate of a weak base, then you would expect it to be more soluble in basic solution. So an example that comes to mind quickly would be ammonium. So if you had some kind of ammonium salt, then we would expect that to be more soluble in basic solution because of a very similar process here, except with the base instead of the acid equilibrium at play. Okay, So what should I be able to do with this? So you should be able to determine if the solubility of a salt will be impacted by the pH of the solvent, and you should be able to discuss this impact qualitatively in terms of the Chatelier's principle. And that, my friends, is it for Unit 8. And so I will see you soon for Unit 9.